So standing waves are a type of wave where at least one place in it is fixed, and they trap energy inside the standing wave. So that's relatively easy to see when you have a wave on a string, which may be fixed in someone's hand, or if it's a musical instrument, it could be attached by pegs or other means, so that it's not free to move however it wants. That's why, for example, when we use a very, very, very long spring or a rope, and once someone holds one end, the resulting wave amplitude that you get is so much bigger than the amount that you're moving your hand. So you can be moving your hand a relatively small amount, but the middle of the wave will be much, much bigger. It's because it's trapping the energy in there. And what's happening is the wave, say I'm moving this end up and down, the wave moves along the spring or the string, hits the barrier at the other end and comes back. And what you get is a reinforcement cycle. So as my wave, let's say it's like this, comes in, it bounces off. But by the time it's bounced off, it's met another bit of wave, and you get reinforcement happening. And the same thing can happen in pipes, although it's not obvious how it happens in pipes. You can't actually see the air particles moving backwards and forwards, but you're just going to have to imagine that at the open parts of pipes, it's easy for the waves to move backwards and forwards. You can get big compressions, big rarefactions, and so with a standing wave in a pipe, you end up getting antinodes. All right, so the interesting thing about this is that, and we'll just look at ones on strings for now. The interesting thing about this is that the waves only certain waves can fit. You know, if you've got to have a node here and here, there's only a limited number of waves that you can fit. You can't get any wavelength on it. And you would know this from trying with holding the spring or holding a long rope. You would know that sometimes when you move your hand with a certain frequency, you just end up with kind of incomprehensible, like wave-like things happening. You don't end up with a nice wave. So I hope you can see that the simplest wave that can possibly form is going to just have one half of a wave. And it's going to go up and down like that. Okay, that is the fundamental wave that can form on a string, and it's the simplest. That's why it's called the fundamental, the simplest. Sometimes you'll see it called the first harmonic, and this will be important when we're talking about harmonics in general. Okay, and I hope you can see, looking at this, this is half a wave, so that means that the wavelength is twice the length of the rope for the fundamental. Okay, the most basic wave is twice the length of the rope. Now I'm going to do a second wave, okay, and I'm just going to draw the point this time rather than the wall. This time, oh, not very good drawing on my part, but we'll roll with it. This is the second harmonic. This is the next most simple wave that can form on the string, since these 2 points here have to be nodes. And I hope you can agree that in this case, the wavelength is simply the length of the string. But I'm going to write it as 2L over 2. See, second harmonic, and these 2's will cancel out. The reason for that will become obvious when I just squeeze in the third harmonic here. This time, and let's hope I do a good job of drawing it, this time we're going to have a peak, a trough, and another peak. And this is going to be the third harmonic. Okay, I'm not worried if this squeaks off to the side, because you'll know that's the third harmonic. And in this time, the wavelength is going to be 2/3 the length of the wave, of the string rather. Now, I hope you can see that we can go on and on and on with this. We can get a huge number of harmonics. And in fact, the thing that makes a difference between different instruments is the way that the harmonics behave. So some instruments have mostly the fundamental or the first harmonic. Some instruments produce a huge blend of harmonics, and that affects the sound quality we hear from them. But it's not just standing waves on strings. So not only stringed instruments demonstrate harmonics, pipes do too. So open pipes are fairly easy. So if I draw an open pipe like this, I'm going to make it quite short this time. If I have an open pipe, there must be an antinode there and an antinode there. And even though it's not easy to see, you're going from a peak to a trough. So that's going to be half a wavelength again. The wavelength is 2L. Okay? Now, if we go further and further and further on, and I'm going to change to another colour because that red's getting hard to see for me. If we go further and further and further on, we must always have antinodes. So this time, we must have a peak to a peak, or a trough to a trough. And I hope you can see again that the wavelength equals 2L over 2. Okay, and hopefully you've spotted the pattern for an open pipe as well. When I say that we're going to see what the third harmonic looks like, you should already be predicting that the third harmonic is going to be, 2/3. So this one is a little bit trickier for me to draw, but let's hope I can do it. Okay, one wave, and a half. So the wavelength is 2/3 of the length of the pipe. Okay, closed pipes are a little trickier. Okay, closed pipes must have a node at this end and an antinode at that end. Okay, so here's our first harmonic. Okay, and you can see there, this time, the wavelength is 4 times the length of the closed pipe. So closed pipes are the exception, and the reason for that is we don't draw the second harmonic. We skip the second harmonic and go straight on to the third harmonic, because I hope you can see that after this, if there has to be a node there and there has to be an antinode there, our next harmonic, the next one that can possibly fit in the pipe, must have fit like this. Okay, peak, trough, node. And I hope you can look at this and see, well, there's half a wave and there's like a quarter of a wave. So this one is like, it's not like a second harmonic. A second harmonic is a full wavelength. This isn't a full wavelength yet. And we would write that okay, because it's 3/4 of a wavelength. Okay, 3/4 of a wavelength, which means it's going to be 4/3 times the length. One wavelength is going to be 4/3 the length of the pipe. So that's a third harmonic. So for closed pipes, only the odd numbered harmonics turn up for reasons. If you're interested in learning more about this, we can talk about it in class.